Alright, so far in Chapter 5, we have learned about the process of anti-differentiation, which is the process of taking a derivative function and working backwards and finding the antiderivative. And within that section, we introduced the idea that the process of finding an antiderivative is called integration. And we found some symbols and some information about determining an indefinite integral, which is essentially the antiderivative. And then we started looking at a special case or application where we were using Riemann sums and rectangles to find the area under a curve or between a curve and the x-axis, and that this limiting process that we applied actually created what was basically a definite integral, an accumulation of area from a low bound A to an upper bound B. And so we've kind of been playing around with kind of what this idea of what is an indefinite integral and what a definite integral is. And really what happened was these two branches of calculus, this differentiation and this integration, were developed separately. And it wasn't until Isaac Barrow discovered that these two processes were actually inverse operations of each other. And so his idea is that, and I've been kind of coaching you all along, so it might seem obvious to you, but that the idea of finding this area under the curve using this definite integral and this process with the Riemann sums actually is directly related to the antiderivative and the differentiation process that we were using to work backwards in section 5.1. And so he's credited with kind of making the connection. And then it was Newton and Leibniz, of course, who then exploited the idea that he came up with and have developed calculus into the form that it is today. So what we're really looking at in this section, this is our first foray into, now we're ready for the shortcut rules. Now, prior to this, we've been kind of saying that if you could do a definite integral and calculate it by looking at the geometry and using geometric formulas, then you would do that. Or if we could use the picture and we knew some information and we had some properties of these definite integrals, if I had given information, I could then find some definite integrals. But what we really want to do is kind of exploit the idea that the definite integral is calculating your accumulation of area, your net change in your position function if you're trying to use a definite integral with a velocity function. Alright, so before we go on and we actually start stating what the fundamental theorem of calculus is, I'm just going to remind you to please review these basic rules that we've had so far, that if we are integrating and there's a constant, we can pull it out. If it's the antiderivative of a constant, then that would be kx plus c. And notice these are indefinite. Notice I'm not talking about the definite yet. I'm talking about these indefinite integrals. These are these antiderivatives. The derivative rules backwards. If I have x to a power to work backwards, I add 1 and divide by the power. The antiderivative of e to the x is e to the x. And remember, we're doing the plus c because those are the general antiderivatives. If you'll remember that we would need to be given some information to set which antiderivative you're on. Make sure you pay attention to like the antiderivative of 1 over x or x to the negative 1. Don't confuse it with the power rule working backwards. Remember that that's the derivative of a log. And then remember that we put in the absolute value bars because we're trying to preserve the domain of the integrand. When you look at your x to the negative 1, it's not defined at 0. And so when we go backwards, we want to make sure that we get a function that is defined at the same places that this is defined. So your log, if I didn't put the absolute value bars, would only be defined for positive values of x. And we need it to be defined for both positive and negative, which is why the absolute value appears there. Here's your antiderivative for your b to the x. Remember that if you were to take the derivative of b to the x with respect to x, that it's itself times the constant natural log of b. So of course, if I'm working backwards, if I've got something that is the derivative b to the x, then I must have to have been dividing by that constant, dividing it back out. Our trig, we want to make sure we get our trig derivatives and our antiderivatives in our knowledge bank. And then, of course, we have our inverse trig ones that we want to take a look at as well. All right, so what we're going to do now is we're going to now introduce the fundamental theorem of calculus. Now, the fundamental theorem of calculus is actually something I've been building toward this entire time. That when we were working on our definite integral, so now I'm not doing the general antiderivative that we were doing on the previous page, I'm talking about this definite integral, which is your net change. It's your accumulation of area. And that the idea is that the accumulation of area, and again, I think the easiest example is to think of this as a velocity, a position velocity curve. So if you're given a rate curve, okay, so you're given a velocity curve. If you are given a velocity curve and you're calculating the area or the accumulation of area under the curve from A to B, the units of this area is going to be your change in x, which is going to be, for example, if this is in miles per hour, then your delta x is going to be in hours. Your height of each one is going to be your rate, your miles per hour, and if I take my miles per hour times my hours, I get miles traveled, which is my displacement, my change in position that we are looking at. And so this idea really should make sense to us that if I want to calculate a definite integral from a to b of f of x, I am looking for the net change in my original function. So I can calculate the antiderivative, right? Antiderivative. This is where that if I were to take this capital F and take its derivative, I would get the integrand in the definite integral. And that what we're going to do is we're going to calculate net change. So I need to know the value of the position function at b at the end of the interval and the value of the position function at the beginning of the interval. And if I take the difference between the two, that would give me my net change. Now, make sure you're paying attention to the difference in notation here. If I were to say antiderivative of f of x dx, if I'm doing an indefinite integral, I know that I'm doing an indefinite integral because there are no bounds. Then I know I'm calculating an antiderivative, and then you add plus c to it to make it general, that there are many functions that could be the position function. There's a certain constant of integration in there. But as soon as we see that we have bounds on this and we know that we're doing a definite integral, then we know that we're only looking for the net change. So I'm not necessarily looking for a position function, I am looking for the net change in the position function. I can use an antiderivative. This actually could be any antiderivative. Typically, we're going to actually pick the easiest, the one where the constant is 0, but we basically can find any antiderivative. And this part right here is showing that we know that we're not finding a general antiderivative or a specific one, that we're still doing a definite integral. So we're showing that we're going to evaluate this antiderivative on the interval a to b, that we're going to be looking for the net change in a to b. So we have to put this on to show that we know we're doing net change. And how do we do it? We then just plug in the endpoints into our antiderivative and calculate the net change. So it turns out that these two processes, the taking the derivative and finding the net change, are very much related to each other, and that's what the fundamental theorem of calculus, the first part, is going to tell us. So if I want to evaluate these integrals using the fundamental theorem of calculus, then basically what I'm going to do is simply find the antiderivative of each of these. I'm going to ignore the definite integral part of it. I'm just going to go to section 5.1. The antiderivative of e to the x is e to the x. The antiderivative of a constant would be minus 3x. And then instead of going plus c, if I was doing an indefinite interval, I show that I know that I'm doing net change by showing my bounds. And then I actually calculate them. I just plug in 3, e cubed minus 3 times 3. That's the value of the antiderivative or your position function at the beginning or at the end of the interval. And then we subtract the value of the position function at the beginning of the interval, e to the first minus 3 times 1. And then we simplify, do your arithmetic that's going to simplify. We end up with e cubed minus e and then minus 9 plus 3, so minus 6. So you get a value for that. And now it becomes something fairly straightforward as long as you understand your derivative rules and your anti-differentiation, your integration rules from section 5.1. Same thing here. First thing you want to do, and we still use some of these properties, this is really a constant times a known derivative. I'm going to pull out the 2 because I know that 1 over the square root of 1 minus x squared is a known derivative, and that is the derivative of your inverse sine function. So I now find the antiderivative. The antiderivative of this is inverse sine of x. Now I'm not doing general, so I don't need to do plus c. I show that I know that I'm doing a definite integral and calculating net change by showing my bounds. And then I calculate the net change. I plug in the 1/2, so I would have 2 inverse sine of 1/2 minus 2 inverse sine of 0. And then of course you've got some trig calculation. The angle whose sine is 1/2 is pi over 6. The angle whose sine is 0 is 0. So we end up with a final answer of pi over 3. So again, we can find the net change. We can find the accumulation of area simply by using the antiderivative and then calculating the net change. All right, so let's take a look at this one. Now be careful when you see x to the negative 1. You are going to be tempted to do a power rule working backwards, but you're going to remember that this is a known derivative. X to the negative 1 is our derivative of the log, and then we also recognize that we need to preserve the domain, that we want to make sure we can do positives and negatives. We put in our absolute value, and we are evaluating this from 1 to e squared. So I show that I know that I'm doing net change by showing the bounds, and then we calculate it. Natural log absolute value of e squared minus natural log absolute value of 1. Absolute value of e squared is e squared. The natural log of e squared is 2. And the natural log of 1 is when you would have had e to the 0, so that's minus 0, and we get a final answer of 2. So this is going to be our shortcut for creating and finding the net change or finding the definite integrals. We are going to use antiderivatives that we know, and we are going to then calculate the net change in the antiderivative. All right, so let's take a look at example 2 and kind of work through those. And again, we kind of cheer when we get polynomials because those are the easiest thing to take the antiderivative of. So we take the antiderivative, add 1 to the power, and divide. And then constant, so minus 3, which is essentially still adding 1 to the power. Put your parentheses and show that you know you're doing net change by showing that you're going to be evaluating this at the bounds. And then you plug and chug with your bounds. 1/3 times 2 cubed minus 3 times 2. That's plugging in, that's calculating your antiderivative at 2. And then you are going to subtract your antiderivative at the other endpoint of your bounds at 1. And then we can calculate what this is going to be. So we're going to end up with 8/3 minus the 1/3 over here. I'm just putting my common denominators together. Minus 6 and plus 3. So we end up with negative 3 plus 7/3. And making myself do some arithmetic here. I need a common denominator, so this would be negative 9 plus 7, so negative 2/3. So yeah, there's a little bit of arithmetic involved, but not much. We can find that accumulated area by finding the net change in the antiderivative. All right, let's do the same thing here. And remember, this is x to the 1/2. I'm going to pull the constant out that has no bearing. And then we're going to take the antiderivative of x to the 1/2. So I add 1 to the power and then divide by the power, which would be the same as multiplying by 2/3. And then we show that we know that we're doing a net change by showing the bounds that we're going to evaluate it at. And then from that point we can simplify, and we're just going to plug and chug. I'm going to put in the 4. So I would end up with 2 times 4 to the 3/2 minus 2 times 1 to the 3/2, my net change in my antiderivative. So this would end up being 2 cubed, which is 8. 8 times 2, 16 minus 2, or 14 would be our accumulated area for that definite integral. All right, and I'm leaving you to verify on the calculator on your own. You can use the function int to show that these are true. All right, so we look at this one. And again, we recognize that the integrand is a derivative we know. Secant squared is the derivative of tangent. So if I go to calculate this, I go, hey, I'm going to take the antiderivative, tangent of x, and again, I'm not doing the general. I'm showing that I know I'm doing net change. So the definite integral is equal to the net change in the antiderivative, which is then simply going to be plug and chug. Tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. Our final answer is 1. All right, now if you have an absolute value in there, I would encourage you to recognize that the bounds are going to play a role on this. Remember that absolute value of 2x minus 1 is going to be 2x minus 1 when the quantity is positive, and it's going to be the opposite of 2x minus 1 when the quantity is negative. So now we need to figure out when it's positive and when it's negative, which would be when is it 0? It's 0 at x equal to 1/2. And if I pick a number before 1/2, say 0, it's going to be negative. So this part is x is less than 1/2, and this part would be the x greater than 1/2. You want to make your life easy and realize that when we do this problem and we're doing this definite integral, we actually have two things that we have to calculate. We have to calculate the integral using this up until we get to 1/2, and then we're going to have to integrate using this after we are at 1/2. And it's going to matter because 1/2 falls in this interval. So I'm going to split this kind of like a piecewise. I'm going to recognize that I'm going to have to go 0 to 1/2, and that one is going to use the left piece of the absolute value, so negative 2x minus 1 dx. And then I'm going to add that going from the 1/2 all the way to 2 on the other piece of the piecewise function, which would be 2x minus 1 dx. So you basically have to, when you see absolute value as an integrand, you have to determine the two pieces that make up the absolute value and then determine which piece you're using for the bounds on your integrand. So we'll come down here. We'll take the antiderivative because we're going to do the net change. This is negative 2x, so the antiderivative would be negative x squared. And then this will be plus 1, so plus x. And we're going to evaluate this net change for the first part from 0 to 1/2. And then we're going to add to that, and notice that your antiderivatives are fairly close to each other. The antiderivative of 2x is x squared minus x, and we're going to evaluate that one from 1/2 to 2. So that will give us kind of this idea of what we're looking for. and we basically plug and chug. We find the first antiderivative and plug in 1/2. So we would have our negative 1/4 plus 1/2. And then we find net change, subtract when we plug in 0, which hopefully you can see you're going to get 0. And then add that to the net change in the second part. We plug in the 2, so we're going to get 4 minus 2, minus, when you plug in 1/2, which is going to be 1/2 squared, so 1/4 minus 1/2. And we do have some nice cancellation happening here. We're going to have negative 1/4 minus 1/4, so that's going to be negative 1/2. You have 2 here, and then you have 1/2 plus 1/2, which is going to be plus 1/2. So these two cancel out, and we get a final answer of 2. And like I said, I'll leave you to verify that on the calculator. All right, let's take a look at example 3. And again, it doesn't really matter how complicated these are. We're going to remember that constants we can pull out, we can distribute integration over sums and differences, and we look for known derivatives. So when I'm doing this problem, I'm going to go ahead, because hopefully you can recognize that this right here is a known derivative, and that 5 over x is the same as 5 times 1 over x. You don't have to necessarily write this step. I'm going to write it just to kind of show you that you can integrate from 1/2 to 1 over e of the 10x to the 4th minus, I'm going to pull the 2 out and rewrite this as 1 over the square root of 1 minus x squared, a known derivative. And don't forget, when you're distributing, each time you write an integral symbol, you got to match it with dx. And then minus, I'm going to pull the 5 out, integral 1/2 to 1 over e of 1 over x dx. That what you're doing is you're trying to use the rules that we have and make sure you have integrands that are known derivatives that you know from chapter 3 and in 5.1 when we were doing this. So power function, add 1 to your power, and then divide by 5. 10 divided by 5 is 2. Now, since these bounds are the same, like I said, this step is kind of unnecessary if you can see it as you are looking at it. So I don't really want to go bound 1/2 to e. I'm just going to stick it at the end. It's the same bound on every one of them. Over here, they had different bounds, so I kind of split those up. So I'm going to go 2x to the 5th, and then here, minus 2. The antiderivative of 1 over square root of 1 minus x squared is inverse sine of x. Minus 5, antiderivative of 1 over x is natural log, absolute value of x. Put your parentheses and show that you know you're doing net change by evaluating it 1/2 to 1 over e. And then we just simply have to plug and chug. So we have 2 times 1 over e to the 5th, or 2 over e to the 5th, minus 2 times the inverse sine of 1 over e, not something I'm going to know, not special, minus 5, the natural log of 1 over e. Absolute value of 1 over e is 1 over e, which is e to the negative 1, and the natural log of e to the negative 1 is going to be negative 1. So that's my antiderivative evaluated at 1 over e, minus net change, my antiderivative evaluated at 1/2, so I would get 2 over 32, or 1/16, minus 2 inverse sine of 1/2, which is pi over 6, minus 5 natural log of 1/2, because I don't need the absolute value anymore. And then from there, we'll just say that you can collect like terms and simplify as needed, but that part is not as important on this. The process is use your properties of integrals, find known antiderivatives, or find known derivatives inside your integrand, take the antiderivative, and calculate your net change. All right. Now, coming back to our idea of area, and remember that area and the definite integrals are not the same. They are related to each other. We can use definite integrals to find area. We can use areas to find definite integrals. So we want to pay attention when they're asking us to use definite integrals to find this. The first thing you would do in all of these problems is to make a nice sketch so that you know what region you're looking at. So we have a parabola that has been shifted down 1, okay, which has x-intercepts of 1 and -1, positive 1 and -1. And we're going 0 to 3 to 3, so I might as well get, when I plug 3 in, we're going to get 8. So 1, 2, 3, 4, 6, 7, 8. Right? And so, yes, the parabola would come around and continue through here. It's not a great picture of my parabola. Okay, and we're going from y equal to 0. Now we have to always remember in our head y equal to 0 is the x-axis. So now I'm going to go ahead and start trying to figure out my area that I'm looking for. So I'm finding the area bounded by the parabola, the x-axis, x equal to 0, up to x equal to 3. So now notice that because this is above and below, that when I am going to calculate this area, I have to recognize that the area using the definite integrals, that you're going to have a problem for this first section. So I'm going to take the integral from 0 to 1 first of my function x squared minus 1 dx, but I have to remember that the definite integral is going to be negative, and I want area, so I make it positive by putting a negative in front. And I'm going to add to that the area from 1 to 3 of x squared minus 1 dx. So that's how I'm going to do it without a calculator. And I'm going to use my fundamental theorem of calculus now. I'm going to take the antiderivative. The antiderivative of x squared is 1/3 x cubed minus x. Don't forget that there was a negative out here in front. We're going to calculate the net change in the antiderivative from 0 to 1, and then I'm going to take from 1 to 3. The antiderivative is exactly the same, 1/3 x cubed minus x, and only this time I'm calculating net change from 1 to 3. So, and I'll leave you to go ahead and do the plug and chug on this, but you basically plug in your 1. Well, actually, let's just do it. It's easy enough. So I would have negative times 1/3 minus 1. That's your value of the antiderivative at 1, minus your value at 0, which is going to be 0. So your net change on the first part is going to give us negative 2/3, positive 2/3. Notice how it turned into a positive number because I'm calculating area. The definite integral was negative, but then we made it opposite to make it positive. Then I plug in my 3, so this would give me 27 over 3, which is 9 minus 3, minus, put in your 1, 1/3 minus 1. So this would give us 6. This is negative 2/3 plus 2/3, so we end up with 6 4/3 or 7 1/3 for a final answer. Now, if I'm going to do this with a calculator, though, I am not going to split it because I recognize that the alternate way to find area, if you will recall, is to simply go 0 all the way to 3 and to take my function x squared minus 1 and to do absolute value. I don't really want to do this if I'm doing it by hand, because if we go back to the example that we did over here, then I would have to define the absolute value using the pieces, figure out what pieces I have, and then end up having to do the opposite of one of the pieces. And right there, that should tell you you're going to end up right back with this formula right here, because you'll find that 1 is where it switches from being positive to negative, and then you would have coming here. So there's no point to write this and then figure it out with absolute value. It's easier just because you already had the sketch, you already know where to split it. But on the calculator, I would just grab my calculator at this point and choose my math in number 9. If it's going to work here, I might have to pause this and see what's going on. Alright, I'm going to pause, shut it down, and restart. Alright, so after having restarted, we would choose the math button. We're going to choose number 9. We're going to put in our low bound and our high bound. We're going to go absolute value, so go back to your math menu and go get your absolute value command, and then put in your function, x squared minus 1, and we're differentiating with respect to x, and then we should get our same answer, 7 1/3, that we got before. Now don't freak out that this is a little off over here. Remember, this is a numeric approximation from the calculator, kind of like a Riemann sum, and so it may be off a little bit, but we'll verify, we've already verified that it's exactly 7 1/3. Alright, so everybody's okay with that part, and so the idea is to remember the big main idea is that definite integrals can be used to find area, and area can be used to find definite integrals, but they are not exactly the same. And now that we have the fundamental theorem of calculus, we can now calculate these areas exactly by hand using the fundamental theorem of calculus. Alright, so let's take a look at this one. We have a region bounded by the curves. So again, first step is always to sketch. So I have y equal to 0, which is my x-axis. I have 2 to the x minus 1, which has a horizontal asymptote at -1 and a vertical asymptote at 0. This is your hyperbola, your good standard 1 over x that has some transformations in it. Let's get some points. We're going from x equal to 1, so I might as well plug 1 in, which is going to give me 2 minus 1 or 1. So 1, 1 is going to be on it. And if I plug in 2, I would get 0. Okay, that's always good. That was a good happenstance there. And then, of course, we're going to go all the way out to e, which is, here's 3, so e is a little bit shy of that. I actually don't need to know what it is because we know that the function is coming in and doing this, and then the piece over here, of course, from our hyperbola would be over here. Now what I'm concerned about is the area of the region bounded by the x-axis, x equal to 1 and x equal to e. So we're essentially looking at those two little yellow sections that we're looking at. So again, as we work this problem without a calculator, we realize we have to split because it's above and below. And where did we split it? At x equal to 2. That was nice when I was plugging in. I found out when it was equal to 0. So without a calculator, the area is going to be equal to the integral from 1 to 2 of the function 2 over x minus 1 dx plus, then when I do the integral from 2 to e of 2 over x minus 1 dx, that's going to be a negative value because the function's below, so I do the opposite of that to make it positive. Alright, now when I'm calculating my antiderivatives, remember this is 2 times 1 over x, so it would be 2 natural log absolute value of x, antiderivative of 1 is x. We're evaluating this antiderivative for the net change between 1 and 2, minus same function, so 2 natural log absolute value of x minus x, evaluated from 2 to e for net change. And so we would simply go through and plug in our values. 2 natural log of 2 minus 2 minus, plug in your 1, 2 natural log of 1, e to the 0, that's times 0, minus 1. Put your parentheses, don't forget net change. And then we're going to have minus. Now be very careful with this minus. You can distribute it and then do net change, or do net change and then distribute. You might want to put a big parentheses right here. So we're going to plug in e. Natural log of e is 1, so 2 minus e, minus, plug in your 2 natural log of 2 minus 2. And notice I'm dropping absolute value when it's a positive number if you're wondering where it went. And then I combine like terms, and the nice thing about this is, notice we've got 2 natural log of 2 here, and then coming along down here I have a 2 natural log of 2 there, and I'm going to distribute the negative through, so I end up with 4 natural log of 2. Then I'm going to have minus 2 minus 2. This is minus 4, or sorry, this is gone. Minus 2 plus 1, so that's minus 1. Minus this 2, okay, so that's minus 3. And then distributing this over to here, plus 2 again, so I'm back at minus 1, I believe, minus 1. And then let's see, what else? It would probably be easier if I would have written it down trying to do it all in my head. I've got a plus e here that I need to worry about. So I took care of this. We took care of this, technically, this 2, and did I forget a negative? You know, I did, didn't I? Right there. So this would be 2 plus 2, or 4 here. Let's just simplify this. Minus e minus 2 natural log of 2, and then we're subtracting it, so it ends up being negative 4 plus e plus 2 natural log of 2. So the 4 natural log of 2 is correct. I have a minus 2 and a minus 4, so I actually have minus 6, and another minus 1 makes it actually minus 7. The hard part is the arithmetic. All right, actually I'm going to stop trying to shortcut, and I'm actually going to just write everything out to make sure I get it right. So I have 2 natural log of 2 minus 2, and then when we plugged in 1, just making sure I'm checking my math, natural log of 1 is 0, so we end up with plus 1. And then over here we plugged in e, natural log of e is 1, times 2 is 2, minus e, and then we subtract, plug in 2, minus 2, so this is going to end up being minus 2 minus e minus 2 natural log of 2 plus 2, which is going to be 2 natural log of 2 minus 1 minus 2 plus e plus 2 natural log of 2 minus 2, which gives me 4 natural log of 2 minus 5 plus e. All right, let's verify that that's right. All right, so if we check this in our calculator, okay, so I'm basically going to do my 4 natural log of, let's clear, 4 natural log of 2 minus 5 plus my e, okay, which is what we just found using the by hand method, 4 natural log of 2 minus 5 plus e. We get an area of 0.491, okay? So approximately 0.491. So let's remember that, approximately 0.491. So now if I want to put this in my calculator and I'm finding area, then I need to remember that when I put it in, the area is the integral from 1 to e of the absolute value of 2 over x minus 1 dx, because I'm doing area, not definite integral. So then we go back to our calculator, and we put that in. So we do our math, and our 9, we're going from 1 all the way up to e. Well, don't forget the absolute value. I'll give you a little heads up. I've been sitting here for 10 minutes trying to figure out why I wasn't getting the same answer, and I had forgotten the absolute value, which of course the definite integral and area are not the same. You have to remember to put in this absolute value, 2 divided by x minus 1, and then our dx, and we get thankfully, the same answer, or approximately the same. Remember, this is a numeric approximation that the calculator is doing. This was the exact value that we found using the fundamental theorem of calculus. Right? And then one last thing before we kind of end this set of notes, that a lot of times that if you know something about the symmetry of the graph, then that's going to help us shortcut a little bit when we're doing integration. Mostly because when we're doing it by hand, to do this integral, and we're trying to find the region bounded by the x-axis and the function, that what I would do is do the integral from -1 to 1, and then we would have our -20 over x squared plus 1 dx. And what we would recognize here is that if we were going to do this, we would pull the 20 out. We have a known antiderivative for this. The 1 plus x squared dx, that is a derivative of our inverse tangent. And so we recognize we have a known derivative. And then we would do our antiderivative, right, which would be 20 inverse tangent of x, and we're evaluating it from -1 to 1. And you might be like, all right, well, this isn't that bad. But one of the other things that you want to recognize is sometimes when we're doing things that plugging these values in, I don't necessarily have to plug in both of the values to calculate the net change. That if I'm looking for this area, and notice, what do I know about this function right here? This function is an even function. And so if you have even symmetry, and in even symmetry, I just realized I didn't have my microphone on. So this would be the long way of doing this. And then, of course, we would do 20 inverse tangent of -1 or +1 minus 20 inverse tangent of -1. So that's kind of the longer way to do this. If you recognize that you have a symmetric function over here, that there's even symmetry, and that I'm doing around -1 to 1, then I know that I can actually do bounds of 0 to 1 and then just double it. And that will work exactly the same. If the function had been odd, okay, and again, I'm stressing this for a reason. If the function had been odd, then I wouldn't have done anything at all, because I would definitely know that the accumulation is going to be 0. All right. The other thing that we need to worry about is whether or not we're above or below. Right now, this is finding the accumulation of area. But if you look at this, this is always negative. Always negative. And so I really need it to be always positive. So I'm going to go ahead and do a plus right there so that I don't have to worry about that. Notice I kind of automatically did it here. You might have been going, hey, she didn't do her absolute value. Technically, I really needed to do this because I want to find area of the region. And so now here I'm finding area. I'm still doing the absolute value, but instead of having to plug in -1 and 1, it's sometimes a little easier to go ahead and simply plug in 1 and 0. Inverse tangent of 1 minus inverse tangent of 0 is 0, so that goes away. It just makes it a little bit easier. There will be maybe a multiple choice question where you know some information about the symmetry of the function, and you're going to use that to help you evaluate the integral. If I have even symmetry, the integral from -a to a of f of x dx is always equal to twice the integral from 0 to a of f of x. And that works whether you put absolute value in to make it an area or not. So that's one thing to look at. And then if you had a function that has odd symmetry are always opposite sides on either side of the origin. So if you were doing -a to a of a function that was odd, then you wouldn't do anything. You would simply say that it's equal to 0. All right, so we're going to stop this first set of notes here. That would be your explanation for the fundamental theorem of calculus, part 1. The next set of notes we'll pick up, and there is a part 2 to the theorem, and so we'll leave that for its own lesson.